Hi, we're going to go over some questions from the Physics for You, page 204 question set that I'd set. And the fifth question asks to find the charge in coulombs when they give you that the charge in microcoulombs, which is 4,000, passes each point in a wire in 50 seconds. So 4,000 microcoulombs passes each point in a wire in 50 seconds. And the question in part A says find the charge in coulombs, not in microcoulombs. So they're essentially asking us to change from 4,000 micro, which is times 10 to the minus 6, right? That's in coulombs, but to make it sensible, so to write it as 4 times 10 to the something instead of 4,000 and then times 10 to the minus 6, right? It doesn't make sense to write 4 million and then times 10 to the 1 or whatever. So to put it on in coulombs would be these three incorporated in there would make the minus 6 3 times bigger, so minus 6 goes to minus 3, and you have 4 times 10 to the minus 3 coulombs, which is for part A. That was very easy. Part B says the current in the wire. The current in the wire, formula for current is just charge divided by time, and the charge we have it there, and the time is 50 seconds. So the current is easy to calculate. 4 times 10 to the minus 3 divided by the 50 seconds that it takes for that charge to go through gives us a current of 80 times 10 to the minus 6, or 80 microamps. So do that in the calculator and see that you get the right answer for that. Part C is the one that I think one of you had trouble with. It says the number of electrons per second passing each point in the wire. So that's the number of amps. That means what's the definition of current or amps? It's the charge per second, right? And so if the total charge per second is 80 microamps, and the question says how many electrons are passing each point in the circuit. Well, if this is my, each point in the wire, this is my wire, then how many little electrons are passing through there has to do with how many amps there are. So if there's 80 microamps, it means that 80 times 10 to the minus 6 amps means that's how many coulombs pass every second, right? So if I want to know how many electrons, I need to know how much charge or how many coulombs each electron has, so that I can divide the total by the number of the charge of one electron, and therefore I can get the number of electrons. So what's the charge of one electron? They give it to you in the question. They say that the charge of an electron is 1.6 times 10 to the minus 19 coulombs. So if I get the total charge passing per second and I divide it by that, 80 times 10 to the minus 6 divided by the charge of one single electron, I get how many electrons I need in order for that current to be a reality. So for that I get 5 times 10 to the 5.0 times 10 to the 14 electrons. You should get, you did it like that. Okay, so hopefully that makes sense. Now the next question that I was asked about was question 16 from the same set of questions. And this is page 205 now. Question 16 says, it's about resistivity. So the question is about nichrome. So they give us some information about a piece of nichrome, and they say that the resistivity of it, which is rho, is equal to 1.1 times 10 to the minus 6 ohm meters. That's the resistivity. And it says that the diameter D is 0.4 millimeters, and that the length is what we need to find out. And in part A they say, well, what is the length of this wire at this thickness that will give me a resistance of 2 ohms? That's what question 1 is, question A, part A is, and then the next one is with 5 ohms. So what do we expect before we do it? Well, a long wire has more resistance than a thin wire. The electrons have to do more work to get through a long wire than through a thin one, and similarly a fat wire has less resistance than a thin wire. So if you had a thin wire, the resistance would be higher than a fat one. So ideal case scenario when you want a low resistance is to have a fat and short wire, and when you want a high resistance, you want a long and thin one. So what do we expect? Well, if we need 5 ohms here, we're gonna, at the same diameter, the same thickness of wire, we should expect a longer length for part B than for part A, since the resistance is going to be higher. What's the equation linking resistance with resistivity? It's just rho times the length divided by the area. But here they give us the resistance and they ask us for the length. So let's rearrange that to solve for the length, and we have the area goes up to multiply the resistance, and the resistivity comes down to the bottom to divide. So this is going to work for both part A and part B. In part A, it's going to look like 2 ohms times the cross-sectional area of the wire. We have the diameter, so what's the cross-sectional area of the wire? It's pi r squared. Pi r squared, and r is half of the diameter, so that's 0.2. Be careful because this is millimeters, so you want it in meters, so that's times 10 to the minus 3 squared. So that's pi r squared. This is the cross-sectional area, and this is the resistance R, right? So that is those two multiply together, divided by the resistivity, which they give us there, 1.1 times 10 to the minus 6. Can't write anymore, 10 to the minus 6 should give you the length. And if you do it in the calculator, you should get a length of 0.23 meters. 0.23 meters, okay? And if you do exactly the same thing, but with instead of 2, a 5 here, you should get a slightly longer length of 0.57 meters. So hopefully that makes sense. Alright, so that's for question 16. And the next one that I was asked about was question 19. So let's have a look at question 19 and change color just for novelty factor. 19. So 19 is about kilowatt hours and energy. It says that there is an electric fire that uses 3,000 watts of energy, and this is how much energy it uses. Okay, there's a certain machine and it uses so much energy every second. So that is kind of it's called the power rating. Okay, you probably can select different power ratings depending on how hot you want it to be and so forth, but here they're telling us that this is how much power the actual machine takes, and that means that that's taking 3,000 joules every second. That's how much energy it's using, 3,000 joules every second. That's what 3,000 watts means. So having told us that that is the power rating of the electric fire that we're looking at, another word for electric fire is a heater. They tell us, okay, so that machine is switched on for a half an hour. Okay, and I'm going to change the half an hour straight away into seconds, just because we're probably going to need that number at some point. So let me just do that. Let's see, so 3 times 60 would be 180, but it's not 3, it's 30. So instead of 180, this is going to be 1 more 0, so that's going to be 1,800 seconds. So we might need this at some point. And now we've got that information. This machine is working for this amount of time, which is equivalent to that amount of time. So having thought about this, the question then says, calculate the energy transferred in joules. So part A says, what's the energy in joules? Well, that's in watts, and that's joules per second, so that's easy because the total amount of energy will be 3,000 watts, which is joules per second, times the number of seconds, which is 1,800. So energy, and this comes from the formula of power, right? Power is just a rate of change of energy in time, or rate of transfer of energy in time. So that's like saying that if you get your power and you multiply it by time, you get your total amount of energy used up. It's the same thing with any rate of change, like current is the rate of change of charge divided by time. So that's like saying that the total amount of charge passing a particular point in a circuit in an amount of time is just the current times the time, because that's the rate of change, and we multiply by the time and you get the total charge. Right? Same thing here. Power is the rate of change of energy with time, or the rate of transfer of energy with time. And so when we divide it by when we multiply by the time, we get the total amount of energy present. So the energy is just going to be then the power times the time, which is the 3,000 watts times the time of 1,800 seconds, and that's going to be quite large, and the answer comes out to be 5.4 million joules. So 5.4 million joules can be written as megajoules, which is the same thing as 5.4 times 10 to the 6 joules, right? Now the second part is based on an idea that we use very often. Well, electrical companies definitely use a lot of the time, and in physics we use it also sometimes. And the idea is that the energy can be measured in this thing called kilowatt hours, right? And the question asks for the answer in kilowatt hours. How do you write it? Kilo is a small k, and watts is a big W, and hours is just written as a small h. So it's important that you write it like that: small k, big W, and small h for kilowatt hours. And what is a kilowatt hour? Well, it's a strange unit, but it's the same thing as energy. It's another measure for energy, right? Why? How do I know that? Well, I just said before that the power, which is what this is, kilowatts, is thousands watts, so that's power, times the time, which is hours, equals the energy. So, in other words, this has the same units as joules, except it will be quite a few joules, but it can be written in joules. So what is 1 kilowatt hour in joules? Well, it's easy to transfer from one to the other. 1 kilowatt hour is the same thing as 1000 watts during an amount of time of 1 hour, which is 60 minutes. So that's 60 times 60. So 60 times 60 is 3,600, and 1000 times that is going to be equal to 3,600 times another 1000. So that is the same thing as 3.6 mega joules, right? Million joules. So 1 kilowatt hour is the same thing as 3.6 million joules. And having done this conversion, we can basically now divide this in 3.6 megajoules and see what we get, and then we'll know straight away how many kilowatt hours we've used. So if we do that, 5.4 megajoules, these will cancel, but anyway, times 10 to the 6 joules divided by 3.6 times 10 to the 6, which should give us an answer of 1.5. And what are we working it in kilowatt hours? So the answer would be 1.5 kilowatt hours. Okay, that's one way of doing it, which is to first find out how many joules is in 1 kilowatt hour and then divide it. A different way is hopefully more intuitive, but it's important that you understand both ways. Another way is to say, well, what is 1 kilowatt hour? 1 kilowatt hour is the same thing as 1 kilowatt power of a machine using 1 kilowatt of power during a time of 1 hour, right? And so if this has got 3 kilowatts, 3000 watts, that would be using an energy of 3 kilowatt hours, right? If it was on for 1 hour, but it's not on for 1 hour, it's on for half an hour. So actually 3 divided by 2 is 1.5 kilowatt hours, and we get the same answer as we got here in a different way. Hopefully both make sense, both arguments. Okay, the next question I want to have a look at is question 20, but I don't have time in this video, so we'll have a look at it in the next video. We'll do 20, 24, and 26 in the next video from the same page 205 in the Physics for You book, and question 20 in particular also asks something about kilowatt hours, so it should be further practice on that. Alright, hopefully that helps. See you in the next video.